Coders, good afternoon. We're gonna look at something after the last time I was talking to Facebook to some people about the pros and cons of C and assembly. Now, one of the things that someone said is that, hey, if I include a library in my C source, that's going to have a lot of functions that maybe I won't use, and they'll still be included in my executable. Someone else was smart enough to say, well, no, that's not true, because compilers and linkers, I think, actually do a dead code elimination, which means that they look for a code that is unreachable and they do not include it in the end result, or they look at libraries that you use and exclude all the objects that are unused in your code. So to demonstrate that, remember that our code last time, let's have a look, the message code. Oh god, I'm opening it. Oh, I already got it open. The message executable was 3K. 3K to be exact, 2200 bytes. The one that we did in assembly was about 60 bytes, so that's a lot smaller. But the library that is there contains a lot of functionality, some of which that we don't use and it doesn't get included. So that's actually a bit of optimization right there that we get right out of the gate. So I got to thinking actually that I wanted to look at recursion, and recursion is something that is shown here. One of the most grateful examples for recursion is calculating a factorial. That's two difficult terms. Recursion is basically a function that calls itself, right? And a factorial is basically math, and it says if I have any value x and I multiply like 1 times 2 times 3 times 4 up to x, the result is the factorial. So for instance, the Windows calculator will have a function type 6, and there's n factorial is 720. So and I was wondering, if I used recursion, how far could I go? Because we've seen by looking at the assembly code that the stack is used a lot. So the stack is used to push variables onto and return addresses, and the stack in the Commodore 64 is only 1 page large, so it's only 256 bytes. So if you're going to use recursion, you're going to be using the stack over and over again until it's full. So I'm wondering, how far can we go? Now, to demonstrate this, I made a little function here. We'll start with an unsigned character and an unsigned character. Let me make some changes here. Unsigned character, because you know, memory locations in the Commodore 64 are just 8 bits, so 1 byte, and an unsigned character is just that, is 1 byte. So what happens here? We have a number here. Let's say well, so we had 6 just now. Let's take 5. We print the size of an unsigned character, so that we know how many bytes are in that. We'll just see that is 1. We'll print it on the next line, and we'll do a carriage return. Knows that. I mean, note that the Commodore 64 doesn't know about lines, right? It's just screen memory is just one big slab of memory, and we're working with lines already, so that's nice. And the factorial is is factor x. So what happens? We call a function factor x. Now we've written that function right here, factor x. It takes x as a parameter. Now if x is 0 or 1, it just returns that, right? It returns. This function won't work on negative numbers, but then we have an unsigned character anyway. So this is just for testing. So otherwise, if it's not 0 or 1, it is a number, 5 times factor x minus 1. 5 minus 1 is 4, so 5 times factor 4. Factor 4 is, we call the function 4, which is 4 times factor 3, which is 3 times factor 2, which is 2 times factor 1, which is factor 1 is, hey, x is 1, we return 1, so we get 1 back. And at that point, we backtrack. All this information has been stored onto the stack. Every time that we call factor, we push our old information onto the stack. And now we go back. So factor 1 equaled 1, so we get 2 times 1, because that's where the function was called. Then this function ends, and we get 3 times factor 2. We go back, we get 4 times factor 3. And 5 times factor 4, and so on and so on. So we use a stack, and each time we call this factor function, as soon as we do recursion, we use the stack, and the stack grows. So let's just see what this does. I'll run it, and we get an int is 1. So an int is not 1. An unsigned character is 1. Anyway, and factorial 5 is 120. Let's we'll do a little check. We'll do 5 factorial. Yep, it's got the right answer. So that's good. That worked. So we did a recursion. If I had to program recursion on the Commodore 64 in assembly, I would have to do a lot of stack operations. And what I've seen in the assembly code that this compiler generates is a lot of support functions that manipulate the stack. So they put a lot of time in getting that correct. But any C compiler should do that, because assembly doesn't know about functions. Assembly doesn't know about parameters. So we have to build that. So that's been built. So if we do, let's say 7, we take 7. So we build. And we run. An unsigned character is 1. Factorial 7 is 176. I don't think so. 7 is 5040. So that's not correct. And you probably already know why it's not correct, because the result of factorial 7 is larger than will fit in 1 byte. So, how do we solve that? We have to go from 8-bit maths to 16-bit maths. So, we don't have that. So, we're going to try an int. Because an int, hopefully, is 2 bytes. This function should return an int, and we also eat one. So let's see if that works. I mean, an integer is not a type that the Commodore 64 knows, and of course I already know that the answer is 5040. And we already saw that. So in the C library, 16-bit maths is already included for free. Well, not for free, because our executable was 2200 bytes large. Let's see how large this factor executable is actually. Oh, where are we? We're here. Factor 3K. Let's look at the number of bytes. 2400 bytes. That's not too bad. 2400 bytes. I mean, it's still large, right? It's still like the character generator ROM, which is sizable. I mean, if you're pressed for space in writing up a game for the Commodore 64, 2K is a lot of sprites. It's a lot of code. So, but on the other hand, it does a lot of things for us already. So if we had to write those things ourselves, it would come down to how well we could write that code, you know, for the trade-off to be in our advantage. So, but I think it's cool that we can do recursion, right? I mean, that's just sort of a gift. So let's see how far we can go. Let's see if we can go 25 deep. Let's run that. I mean, the answer is probably going to be incorrect, right? Factorial 25. 25. Factorial 25. That's an insane number. That's millions, trillions, gazillions. That's a Googleplex. Just saying something there. I don't know. It's a really large number, and we're not, even if we had types like a double, which we don't, or a float. I mean, I've already figured out that the compiler doesn't have floating point support, so we're stuck with ints. But still, 16-bit math for free is pretty cool already. Now, the thing is, the program didn't crash though, so let's see how deep we can go in the recursion. We build it. And we run it. Still going. The result is wrong, but still going. Let's see. Can we go to 75? Can we go to 75? Still going. We didn't crash. We ended. We get a wrong answer, but still correct. Let's go to 90. Run it. Still good. Still good. Let's go to 100. Let's take baby steps now. Still good. I wonder where we're gonna end. 110. I mean, I already saw that 125 was over the limit, so I'm guessing. Oh, 110 still good. 120. I mean, the recursion depth is it depends on how much information I store. So I'm storing an X and a return address. So if I had more to store, 120 still going. I wonder where it's ending. I wonder where. So 125 was too much, I think. Yep. Okay. So that actually crashed. What happened? Oh, it's still. No, it just stopped. We get no output, and we get the prompt, and we go back to caps again. So I don't know what's up there. Why? I don't know why we have small letters. Anyway. We can go up to 120 something recursion depth with a small function. So I think that's impressive. Now, why do I want to do that? And it's because of the fact that I want to be able to write a multiplexing routine for sprites. So the Commodore 64 has only 8 sprites. I can display, the VIC chip can only display 8 sprites on one single scan line. So what we could do, if we have more than 8 sprites, we could, and if we knew their vertical positions, which we would if we were writing a game, we could sort the sprites by their vertical position. Then after we've had a couple, we could sort of use a raster interrupt to say, okay, we've drawn these sprites. Let's change their shapes and reuse them in different locations. Like do a little swap, and then we could have like 16 sprites. It wouldn't be hard, but we would have to be able to sort. Now, if you go online and you look for sorting routines, there are many different sorting routines, and one of the fastest ones that I know of, at least, that I found is Quicksort. Now, I'm not going to explain how Quicksort works, but I have the Kernighan and Ritchie C handbook. And this describes the C programming language. Now, one of the things that I found in there was a quicksort function all written out, so I could just type it in and go. But lo and behold, the standard C library contains a quicksort function, and I don't even have to write it. It's already in there. So I realize now that as soon as I use it, I increase the size of my executable. But let's see what happens. We have our message, right? This is the same message that we had in our first program. This is my message. It's 18 characters, 0 to 17. And what I want to do is I want to print the message, I want to quick sort it, and then I want to print it again. So it's going to sort the letters in the message. The message is going to be garbled, but it's just an example of how sorting works. Now, Quicksort is a function that is in the standard C library, and it takes a couple of parameters. The first one is our message, so a pointer to our message. The second one is the length of the array that we're sorting, which is 18. Then I have to give it the size of a single element. The size of each element is 8 bits, 1 byte, 1 character, so size of character. And I have to give it a comparison function. Now, this is a pointer. If I just mention the name of the function here, I get the address of the function, which is defined here. This fast call bit is a way of declaring functions so that the compiler knows how to handle the call, how to handle the return address, how to handle the parameters. So that's just a part of CC65's calling convention, basically. The name of the function and its parameters. Now, C is a strongly typed language, so every variable has a type, and even variables that have no type have a type called void. So I have two parameters here, one left, one right. They're just called left, and the others are called right, and they are pointers to a void. So basically, I give it pointers to two different elements. Now I have to take the contents of this value. Now, to get the content out of a pointer, if the L value is a pointer, I can use the asterisk to get the value of left and an asterisk to get the value of right. But then C is going to say you cannot do subtraction on two voids. You know that you can't do that with that type. So you have to cast it. So you have to first cast the left, which is a void pointer. You have to cast it to a character pointer so that C knows, okay, the content of left is going to be a character. So then we take the content of the cast character pointer, which is left, and we get a character. Same for right. We subtract them, left minus right. It's just going to subtract the ASCII values and return the result. To quicksort. Now, we don't see the function quicksort. We could look it up, but we only have to provide the comparison function. So quicksort needs this stuff. We give it that. Let's compile and see what goes on when we run it. Look, unsorted. This is my message. Sorted. A bunch of spaces, A, E, G, H, I, M, S's, all the S's, the T, and the Y. It's the same message, but the letters are sorted. So we have a built-in sort routine. How about that? I'm a quick sort routine. So this, you know, you would have to perhaps do some speed tests on it, but let's see how large the quick sort. It's now 4K. Oh, sorry, I should show you. The executable is 3,405 bytes long, but I'm printing, so if this is the second time I'm recording this, by the way, because the first time, whenever you record something, just as an aside, when you record something with OBS, 8 out of 10 times when you start OBS, it says, "Hey, I've got an update." Don't run the update, or if you do, make sure you check all your settings, because all of a sudden I had all my audio input devices recording my voice, so I had my voice 3 times. So this is the second time I'm recording this, just because I ran an OBS update right before I recorded this. So second recording. Back to the matter at hand. Let's just not use cprintf and demonstrate how that affects the size of my executable. I run it. Of course, I get no output because I'm not printing anything, but let's look at, it's now 2K. It is 1,508 bytes. So, the matter at hand is, can we write this program that would sort any array of any type by using Quicksort in assembly in less than 1500 bytes. I'm not sure that I could do it, but maybe one of you can. Is it possible? I don't know. I know there are multiplexes out there, and I'm gonna look for code, and I'm gonna see if I can do this in assembly in less than 1500 bytes. So that's my challenge for the next recording. Thank you for watching, and I'll see you next time. Bye bye.